Welcome to this problem walkthrough. Today, we'll be tackling LeetCode problem number 1639, number of ways to form a target string given a dictionary. In this problem, we'll explore how to calculate the number of ways to construct a target string using characters from a given list of strings. We'll delve into efficient algorithms and key concepts along the way. Let's get started and solve this step by step. In this problem, you are given an array of strings called words, which we'll refer to as the dictionary, and a string target that you need to form. The task is to determine the number of ways to form the target string by selecting one character at a time from any string in the dictionary. However, there's an important rule: each character of the target string must be formed by choosing letters from a specific column in the dictionary. Once you choose a character for a position in target, you move to the next column for the next character. The final result, which can be very large, must be returned modulo 10 to the power of 9 plus 7. The input consists of the array words, where all strings have the same length, and the string target. The output is a single integer representing the number of valid ways to form the target string under these rules. Let's look at an example to better understand this. Suppose words is aka, bbb, kaka, and target is aba. To form the target string, we need to determine the number of ways each character of target can be chosen from the corresponding columns of words. For the first character a, we have two valid choices, one from the first column of aka and one from the first column of kaka. For the second character b, there is only one valid choice, the second column of bbb. For the third character a, there are three valid choices from the third column, either from aka or kaka. When we multiply these options together, 2 for the first character, 1 for the second, and 3 for the third, we get a total of 6 ways to form the target string ABA. Now let's examine another example. If words is Abba, Bob, and target is Bab, we calculate the number of ways as follows. For the first character B, there are two valid choices from the first column of words, one from Abba and one from Bob. For the second character A, there are also two valid choices from the second column, one from each string. Finally, for the third character b, there is only one valid choice from the third column, from ABBA. Multiplying these options together, 2 for the first character, 2 for the second, and 1 for the third, we get 2 times 2 times 1 is equal to 4 ways to form the target string BAB. In contrast, if words is ABCD, and target is ABCD, there's only one way to form the target string, as there's only one column for each character in the dictionary. The problem comes with constraints and edge cases to keep in mind. First, the size of words in target is limited. Words consists of m strings, each of length n, with both m and n being at most 1000. The length of target is also at most 1000. All strings consist of lowercase English letters. Some edge cases include when the target string is longer than the length of strings in words, which makes forming target impossible, resulting in 0. Similarly, if target contains characters not present in any column of words, the output is also 0. For large inputs near the constraint limits, the solution must be efficient to avoid timeouts. Lastly, as the result can grow very large, we return the answer modulo 10 to the power of 9 plus 7 to ensure the output remains manageable and follows the problem's requirements. To solve this problem, we need to determine how many ways we can form the target string using characters from the words array. Each character in the target string can be chosen from the same column across all strings in the words array. One possible approach is the brute force method. The intuition here is to generate all possible combinations of characters from the words array and count the combinations that match the target string. For each character in the target, we look at all columns in the words array and recursively compute the possibilities for the remaining part of the string. While this approach is straightforward and guarantees correctness, it is computationally expensive. Since we have m columns and n strings, the number of combinations grows exponentially with the length of the target string, resulting in a time complexity of O(2)m*t. This makes the brute force method infeasible for larger inputs despite its simplicity. To address the inefficiency of the brute force approach, we can use an optimized method that combines dynamic programming with frequency precomputation. The key idea is to precompute the frequency of each character in every column of the words array and then use this information to fill a dynamic programming table. Specifically, we define a DP table where DP, I, J, represents the number of ways to form the substring of the target starting at position J using columns I to M1 of the words array. To compute this, we look at each column I and the current character target, j. If the character exists in column I, we use its pre-computed frequency to update dp, I, j, based on dp, I plus 1, j plus 1, which represents the number of ways to form the remainder of the target. This approach reduces redundant computations by leveraging the structure of the problem. The frequency pre-computation takes O(m*n) time, and filling the dp table requires O(m*t), resulting in an overall time complexity of O(m*n) plus t. This method is significantly faster than brute force and scales well, although it does require additional memory for the dp table and frequency counts. Based on our analysis, the dynamic programming approach with frequency pre-computation is the most efficient and practical solution to this problem. The key insights that make this strategy work include recognizing that columns in the words array are independent, which allows us to pre-compute frequency counts for each character. This pre-computation, combined with the use of a dp table, prevents redundant calculations when forming substrings of the target. The efficient transition between states in the dp table, where dp, I, j, is derived from dp, I plus 1, j plus 1, ensures computational efficiency. While the brute force approach ensures correctness, its exponential complexity makes it unsuitable for larger inputs. The dp approach, by contrast, achieves a scalable solution with polynomial time complexity, at the cost of some additional memory usage. This trade-off is well justified, as the time savings are significant. In conclusion, this optimized dp strategy is chosen for its balance of clarity, efficiency, and scalability, making it the ideal solution for this problem. To tackle the problem, we need to compute the number of ways to form the string target by selecting characters from the same column across all strings in the words array. Each column represents a pool of characters that can contribute to a specific position in the target string. The challenge lies in solving this efficiently, given the constraints on the size of words in target. First, we start by analyzing the input. The dictionary words is a list of strings, each of equal length m, and target is a string of length n. The task is to determine the total number of ways to construct target using the columns of words, where the result must be returned modulo 10 to the power of 9 plus 7. To achieve this, we pre-process the data to build a frequency table, frequency, which counts how often each character appears in each column of the words array. This pre-processing is crucial as it lets us reduce the time complexity of looking up valid character counts from O(m) to O(1) during the dynamic programming computation. Finally, we define a dynamic programming state to iteratively compute the number of valid ways to form target. The dynamic programming solution revolves around defining the state dp, I, j, which represents the number of ways to form the first I characters of the target string using the first j columns of words. The base case is straightforward, dp 0, j equals 1 for all j, since there is exactly one way to form an empty string. For the recursive transition, we have two choices. First, if we skip column j, the result for dp, I, j, inherits the value from dp, I, j1. Second, if we include column j to form the character target, I1, we multiply the frequency of that character in column j1 by the number of ways to form the previous portion of target, which is given by dp, I1, j1. Combining both cases, the recurrence relation becomes dp, I, j equals dp, I, j1, plus dp, I1, j1, asterisk frequency, j1, target, I1. To compute this iteratively, we initialize a 2D array dp of size, n plus 1 infix, m plus 1, and fill it using the above relation, applying modulo 10 to the power of 9 plus 7 at every step to prevent overflow. The result, which is the total number of ways to form target, is stored in dp, n, m, after processing all columns. The algorithm's efficiency relies on a few key insights. First, the pre-computed frequency table, frequency, is central to reducing the cost of counting valid characters in a column. Instead of iterating through all rows in the words array every time, we can directly access the pre-computed counts in O(1). Next, the dynamic programming approach ensures that subproblems are solved only once and reused, significantly reducing redundant computations. By structuring dp to track substrings of target against prefixes of words, we break the problem into manageable components that build up to the final solution. Additionally, modular arithmetic is applied at each step of the computation to handle the constraints on large results, ensuring correctness while avoiding overflow. The data structures involved include the frequency table frequency, which has dimensions mx26 to account for all lowercase letters, and the dynamic programming table dp, which is sized n+1 x m+1 to accommodate all substrings of target and all prefixes of words. Together, these structures form the backbone of the algorithm, enabling efficient computation of the result. Handling edge cases is crucial to ensure the algorithm works for all inputs. For instance, if the target string is empty, there is exactly one way to form it, which is to do nothing, so the result is 1. If the length of target, n, exceeds the number of columns in words, m, the result is 0 since it's impossible to form target with insufficient columns. The algorithm also naturally handles the scenario where words consists of a single column by iterating over it and applying the frequency counts. Another edge case occurs when none of the characters in target exist in the words array. In this situation, the result is 0 because no valid formation of target is possible. As for complexity, the time complexity is dominated by two parts: pre-computing the frequency table in O, m*26, and filling the DP table in O, n*m, leading to an overall complexity of O, n*m. The space complexity is determined by the space needed for the frequency and DP tables, both of which are O, n*m, resulting in a total space complexity of O, n*m. To further optimize the algorithm, we can reduce its space complexity by replacing the 2D DP table with a 1D array that uses rolling indices. This optimization works because the current state of DP, I, j, only depends on the previous row and the current column, so we don't need to store the entire table. This approach reduces the space complexity from O, n*m, to O, m. Additionally, we can prune unnecessary computations by skipping columns where the frequency of the required character, frequency, j, target, I1, is 0. If a column cannot contribute to the formation of the current target character, we can avoid processing it, saving time. These optimizations ensure that the algorithm runs efficiently even for larger inputs, maintaining the correctness of the result while minimizing resource usage. This solution efficiently calculates the number of ways to form the target string using characters from the words array. We start by extracting the dimensions m, length of each word, and n, length of the target string. Then, we pre-compute the frequency of characters in each column of the words array using the counter class. This allows us to quickly look up how many times a character appears at a particular column. Next, we set up a dynamic programming, DP, array DP, where DP, j, represents the number of ways to form the first j characters of the target string. The base case is DP, 0, equals 1, as there is exactly one way to form an empty string, by doing nothing. The main computation involves iterating over each column of the words array, I loop. For each column, we iterate backwards through the target string, j loop, to ensure that the current state of DP, j, is not overwritten before it is used. If the current target character target, j1, exists in the column, we update DP, j, by adding the product of DP, j1, ways to form the previous part of the target, and the frequency of the character in the column. This value is taken modulo 10⁻9 plus 7 to prevent overflow. Finally, after all iterations, dp(n) contains the total number of ways to form the entire target string. This approach runs efficiently in O, m*n, time, where m is the length of the words and n is the length of the target string, making it suitable for large inputs. Here, we begin the Java implementation of the solution. First, we import the necessary packages and define the method numberWays, which takes an array of strings, words, and a target string as input. We initialize a constant mod with the value 1,000,007 to handle modulo operations for large numbers later. Then, we determine the length of each word in the dictionary, stored in m, and the length of the target string, stored in n. Next, we create a 2D array frequency to store the frequency count of characters in each column across all words. We iterate through each word and populate this array. For example, if a column contains the letters A, B, and B, the corresponding values in frequency will reflect the count of these letters. We also initialize a dynamic programming array DP, where DP, j, represents the number of ways to form the first j characters of the target string. The base case is DP, 0, equals 1, meaning there's exactly one way to form an empty target string. Then, we iterate over the columns of the dictionary. For each column, we traverse the target string backwards to ensure that previously computed states in DP are not overwritten prematurely. If the character in the target string matches one of the characters in the column, we update DP, J, by adding the contribution from the current column, scaled by the frequency of the matching character. This value is taken modulo mod to prevent overflow. After processing all the columns and updating the dynamic programming array, the loop concludes. The final result, which is the total number of ways to form the target string, is stored in DP, n. This value is then cast to an integer and returned as the output of the method. By using this dynamic programming approach, we efficiently compute the result while leveraging the frequency array to reduce redundant computations. This ensures the solution is optimized for larger inputs. The implementation is now complete, and the program is ready to handle the given problem constraints effectively. Let's begin by understanding the first example. Here, the input consists of three words, aka, bbb, and kaka, and the target string is aba. First, we initialize our variables. The length of each word is 4, so m equals 4, and the target has 3 characters, so n equals 3. We also define mod as 10 to the power of 9 plus 7 to handle large numbers. Next, we calculate the frequency of each character in each column of the words. For column 0, we have a appearing 2 times, b 1 time, and c 1 time. Similarly, for column 1, c occurs once, b twice, and a once. We repeat this for all columns. Then, we initialize our DP array as 1, 0, 0, 0, which represents the number of ways to form substrings of the target of length 0 through 3. This is our base case, where there's exactly one way to form an empty target. Now, focusing on column 0, we iterate backward through the target's indices, starting from the end. For j equals 3 and 2, there's no update since the corresponding characters in the target don't match any character in column 0. However, for j equals 1, the target character matches column 0's frequency, so we update dp 1 to 2, reflecting that there are now 2 ways to form the first character of the target. The DP array becomes 1, 2, 0, 0. Next, we process column 1. Again, we iterate backward through the target. For j equals 3, the target character doesn't match any in column 1, so there's no update. For j equals 2, the target character b matches, and we update dp 2 by adding the product of dp 1 and the frequency of b in column 1. This gives dp 2 a value of 4. For j equals 1, the target character matches, and we update dp 1 similarly. The DP array now becomes 1, 3, 4, 0. Moving to column 2, we repeat the process. For j equals 3, the target character matches column 2's frequency, so dp 3 is updated to 8. For j equals 2, the target character b matches, updating dp 2 to 7. For j equals 1, the target character matches again, and dp 1 is updated to 5. At this point, dp becomes 1, 5, 7, 8. Finally, we process column 3. For j equals 3, the target character matches, and dp 3 is updated to 15. This reflects the cumulative number of ways to form the target string. In the final steps of example 1, we finish processing column 3. For j equals 2, the target character b matches the frequency in column 3, so dp 2 is updated to 17. For j equals 1, the target character matches, and dp 1 increases to 6. The final DP array for this example becomes 1, 6, 17, 15. The answer to the problem is the value of dp 3, which is 15. This means there are 15 distinct ways to form the target string ABA using the given words. Now, let's explore the next example, which introduces an edge case. Here, the input consists of 3 single-letter words, a, B, and C, and the target is ABC. In this edge case, we start by initializing the variables. The words have a length of 1, so m is 1, and the target length is 3, so n is 3. We compute the frequency for the single column, which is a 1, B, 1, C, 1. The DP array is initialized as 1, 0, 0, 0. Since there's only one column, we process it directly.
For j equals 3, the target character C matches, but dp3 remains 0 since dp2 is 0.
Similarly, for j equals 2, the target character B matches, but dp2 remains 0 because dp1 is 0.
Finally, for j equals 1, the target character M matches, and dp1 is updated to 1.
The final dp array is 1, 1, 0, 0. The answer to this example is dp3, which is 0. This indicates it's impossible to form the target ABC using the given words.
Let's now consider a longer target string in the next example.
In this final example, the input consists of 3 words, ABC, def, and ghi, and the target is adg. After initializing, we find that the words have a length of 3, so m equals 3, and the target length is also 3, so n equals 3. The frequency of characters in each column is calculated as follows. Column 0 contains a1, d1, g1, column 1 has b1, e1, h1, and column 2 contains c1, if1, i1. The dp array is initialized as 1, 0, 0, 0.
For column 0, we iterate through the target indices. For j equals 3 and 2, the characters g and d match, but dp3 and dp2 remain 0 since their previous states are 0. For j equals 1, the target character M matches, and dp1 is updated to 1.
The dp array becomes 1, 1, 0, 0. In column 1, none of the target characters match the frequencies, so dp remains unchanged. Finally, in column 2, the target characters also don't match, leaving dp as 1, 1, 0, 0. The final output for this example is dp3, which is 0. Meaning it's not possible to form adg using these words.
To analyze the time complexity of this solution, we start by examining the frequency count pre-processing step.
Here, for each column in the words matrix of which there are m columns, we calculate the frequency of each character across all k words. This requires iterating through all k words for each of the m columns, leading to a time complexity of m*k for this step.
Next, we consider the dynamic programming table population.
In this step, the outer loop goes through each column, resulting in m iterations, while the inner loop processes the target string in reverse order, which can lead to up to n iterations in the worst case.
Within the inner loop, we perform a constant time operation to check the frequency map and update the dp table.
Therefore, the time complexity for the dp table population is m*n. Combining the two steps, the total time complexity becomes m*k for the frequency count pre-processing and m*n for the dp table population. Adding these together, the final time complexity is m*k plus n.
Now, for space complexity, we first consider the frequency count storage.
Since we store the frequencies for each column, and each column can have a maximum of 26 entries for lowercase English letters, the total space required for this is m*26, which simplifies to m. Additionally, the dynamic programming table requires space proportional to the size of the target string, specifically n plus 1, which simplifies to n. Combining these, the overall space complexity of the solution is m plus n. When we compare this optimized approach to a brute force method, the differences become striking. A naive approach would involve generating all possible subsequences of the words matrix in column major order and checking which ones match the target string. This would result in an exponential time complexity of 26 to the power of m*n, where 26 to the power of m accounts for all possible subsequences and n represents the time needed to verify each subsequence against the target. In contrast, the optimized dynamic programming approach avoids this inefficiency by using pre-computed frequency counts for constant time lookups and maintaining a single dp table of size n. This reduces the time complexity to m*k plus n, and the space complexity to m plus n, making the solution exponentially faster and far more space efficient. In terms of best, average, and worst case scenarios, the solution remains consistent in its big O complexity of m*k plus n, regardless of the inputs. However, the constants in actual runtime can vary based on the input size. The best case occurs when the words matrix and target string are small, leading to minimal values for m, k, and n, and thus faster computation. The worst case arises with a large words matrix having many columns and words and a long target string, where the constants become large, though the complexity remains O, M asterisk, K plus N. In average cases, with moderate values for M, K, and N, the solution is computationally manageable.
Finally, the mathematical proof reinforces the big O complexity.
The frequency count step takes O, M asterisk K, while the DP table updates contribute O, M asterisk N. Adding these confirms the overall time complexity as O, M asterisk, K plus N, demonstrating that this approach is both efficient and well suited for the problem's constraints. One common mistake when solving this problem is skipping the pre-computation of character frequencies. Without pre-computing, if you directly iterate through the strings in the words list for each character in the target, you end up performing redundant calculations repeatedly. This drastically increases the time complexity of your solution. By pre-computing the frequency of each character for every column and words, you can look up these values efficiently later, saving time.
Another frequent issue is misunderstanding the importance of modulo operations.
When working with large numbers, it's critical to apply the modulo operation, specifically 10⁻9 plus 7, at each step of your calculations. Without it, you risk integer overflow, which can lead to incorrect results or runtime errors. Lastly, failing to handle edge cases, like empty strings in target or words, or when the target string is longer than the strings in words, can lead to out-of-bound errors or incorrect assumptions about the input.
Always account for these scenarios in your implementation to ensure robustness.
Another pitfall is incorrectly updating the dynamic programming, or DP, table. The state of the DP table depends on previous values, so the order in which you update matters. If you update from front to back, you risk overwriting values that are still needed for later calculations. Always update the DP table from the back to avoid overwriting dependencies. Additionally, it's easy to confuse the rows and columns in the words list. Remember, the words list is organized such that each index across all strings represents a column. When working with the target, you need to match characters from the same column across all the strings and words, not treat each string as an independent row. Misunderstanding this structure leads to incorrect results because the problem fundamentally revolves around column-wise frequency matching. This problem combines prefix-based dynamic programming with combinatorics, and understanding this blend is key to solving it effectively.
Pre-computing character frequencies is a classic optimization technique that allows you to avoid redundant computations.
Problems like this often involve modular arithmetic, especially when dealing with large results, and careful updates to your state variables, which are common themes in coding interviews. The optimal approach involves defining a DP table where DP, I, J, represents the number of ways to form the first I characters of the target using the first J columns of words. This structure ensures you can systematically build up to the solution while avoiding unnecessary recalculations. If asked to compare approaches in an interview, emphasize how brute force results in exponential complexity and how pre-computing character frequencies reduces the problem's complexity to O, M asterisk N plus M asterisk T, where M is the number of strings in words, N is their length, and T is the length of target. This problem has connections to several other dynamic programming problems that you might encounter.
For example, LeetCode 115, Distinct Subsequences, shares a similar DP approach for counting subsequences.
It's a good practice problem to build foundational skills for this one.
Another related problem is LeetCode 583, Delete Operation for Two Strings, which focuses on transforming strings using dynamic programming.
LeetCode 97, Interleaving String, involves combining combinatorics and DP to determine if one string can be formed by interleaving two others. Lastly, LeetCode 1048, Longest String Chain, tackles string manipulation and sequence building with dynamic programming.
Solving these related problems can deepen your understanding of the patterns and techniques used in the current problem. While dynamic programming is the optimal approach, it's worth considering alternative methods and their trade-offs.
A brute force approach might involve trying all possible ways to form the target from the strings and words. Although this approach is intuitive, its exponential time complexity, O, M to the power of T, makes it impractical for large inputs.
A recursive approach with memoization can be more manageable, as it avoids recomputing results for the same subproblems.
However, the recursion stack can lead to higher memory usage, which may become a limitation. Another less common method is bit masking, where you use bit masks to represent which characters have been used. While this approach is theoretically interesting, it tends to be more complex to implement and is generally not as efficient as dynamic programming for this problem. Understanding these alternatives can help you discuss trade-offs and demonstrate a well-rounded perspective in an interview. Great job following along. To wrap up, we summarized the dynamic programming approach used to solve the problem and highlighted key takeaways like optimizing nested loops and leveraging efficient data structures. Don't forget to practice similar problems to strengthen your understanding. Thanks for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!